Hello, grade 11s. We're going to talk about the next section of work we're about to start, and it's got a lot to do with solving triangles and trigonometry. So let's just quickly write that down. So we're going to talk about, essentially today, solving triangles. And to give us an example of this from last year, where we did this, if I gave you a right angle triangle, so we spent a lot of time last year talking about right angle triangles, so let's draw one of those. If I gave you certain pieces of information in that triangle, say I gave you the right angle, and let's say I gave you a length of one of the sides, so let's say I gave you the length of the hypotenuse as 2, and let's say that I gave you the angle over here as 30 degrees, then could I work out the other unknowns in this particular triangle? And I would suggest that the other unknowns in this triangle would be the angles on the sides. So I could work out that angle over there is 60 degrees because of the angle sum in a triangle. Now if I wanted to work out the length of the sides, what would I need to think about from last year? What would be the issues we need to consider? Well, we could use trigonometry. So we could go to find the one with the yellow stripe next to it. We could go, well, I actually know that's opposite my original reference angle, and so I could find that by going the sine of 30 is equal to, let's call it the opposite, and the opposite over the hypotenuse, well, the hypotenuse is 2, and so if I wanted to now find the opposite in terms of a value, I would just bring that 2 to the other side, so I'd get 2 times the sine of 30, and what I then find is the opposite would be equal to 1. So that would be equal to 1. Now what more would I need to do to find the other side? Well, if you think about the name of the ratio, if I wanted to find the other side, I would just, let's call it A, I would just say the cos of 30 is equal to whatever that is, so A over 2. And if I now make A the subject of the formula, I can just go 2 times the cos of 30, which I should get root 3 for. And so now I know the length of the other side. So, summarizing grade 10, you learned all the skills you needed to solve a right-angled triangle. Now what's going to be different this year is we're going to take away the limitation of just working in right-angled triangles, and we're going to see, can we solve for the unknowns in any triangle? Okay, so we're going to talk about solving non-right angled triangles. So non-right angled triangles. So what do non-right angled triangles look like? Well, the first type I can think of is an acute triangle, and what makes an acute triangle is that all of the angles are less than 90. So there's not a single angle out of all three which is greater than 90. So that's the one type of non-right angled triangles. And then the other type of non-right angled triangle is obtuse angled triangle, where what makes an obtuse angled triangle is there's one angle which is greater than 90. So those are the two types of non-right angled triangles, the acute and the obtuse. Sometimes people refer to them as the oblique angled triangles. So now what we have to think about in grade 11 is, how do we solve them? How do we solve for unknowns? So a situation, if I sort of use an acute angled triangle, if I give you some information like I had before, so previously I gave you, we had a right angle, we don't have that anymore, but I could say, if I gave you, a 30-degree angle here, and I gave you the length of a side over here, and I had another angle which over here, let's say this angle over here, I'm just making this up, say this one was 70 degrees, could I solve for the other unknowns in the triangle? Now, because of the interior angle sum of a triangle, I suppose most of us could work out that that angle is 80 degrees, but what about the sides over here? What about, the length over here? What about the length of the side over here? Now, previously we had the use of trigonometry or even Pythagoras to help us work out the length of the sides, but now we don't have that anymore. And so what we need is, we need a new tool for the job. We need a new piece of mathematics to help us work this out. So the new piece of mathematics that we're going to learn about that helps us get around this problem is something called the sine rule. And it's very, very clever. So I'll start with the acute angled case of the sine rule, and then we'll progress on to the obtuse angled case. So basically we have this problem whereby we don't have a right angled triangle anymore, and so how are we going to use mathematics to solve the triangle? And the clever way we're going to do it is we are going to take an acute angled triangle and we're going to split it into two pieces by doing a construction. So the first construction is going to be create a perpendicular line from the vertex of the triangle, and what happens is you've now split the original triangle into two pieces, and what you'll find is that the two triangles are actually both right angle triangles. And so now if we solve this triangle by splitting it into two smaller triangles that are both right angled, we can create some new mathematics. So what I'm going to do is I'm going to label my triangle. So I'm going to give it the vertices the name A. Let's rather use a different color. So we're going to go with A, B, and C. I'm going to name the point where my perpendicular line meets the triangle. I'm going to call that D. And then opposite the vertices, we're going to call the line segments, we always name them sort of the little case of the vertices. So opposite vertex C would be line segment little c, opposite here would be B, and the whole bottom length here is going to be A. So now we're gonna show you how the sine rule works. So I'm going to start by looking at the angle B. And, oh wait, let me label one more thing. So I'm just going to label, I'm going to call that red perpendicular line the height of the triangle, because that's what it is. So now what I'm going to do is I'm going to write down the sine of B. If I talk about the sine of B, if I look opposite the angle B, I see the height, and so I'm going to go, the sine of B is actually h, so that's the opposite, over the hypotenuse. The hypotenuse in this case is going to be little c. And, that's pretty much valid from the right angle triangle there. Then what I'm going to do is, if I look now to the angle C, I can now write down that, in fact, the sine of C, and that's the angle C, so maybe I should put little hats on these guys, is equal to, it's also opposite the angle C, it's going to be h, so the height, over, now what's it going to be this time? Opposite, what's the hypotenuse? It's going to be B. Okay, so I've done that. Now what I'm going to do, this next step is quite clever. I'm going to make h the subject of the formula in both of these things. So if I take, for example, the sine of B is h over c, I can actually write that h is equal to c times the sine of B. And over here I can write h is equal to B times ooh, getting a bit messy here, the sine of C. Okay, stop for a moment and think about that. Are those h's the same length in the triangle? Indeed they are. So couldn't I possibly equate those two together? If I did that, what would I get? So I'd get, if I start over here in the corner, C times the sine of B equals B times the sine of C. Oh, that's interesting. So now what I'm going to do is, if I rearrange that even further, okay, what I'm going to do is I'm going to move on to the next page and just work that a bit further. So if I look at that identity that I've worked out, if I now move the C to the other side and the B, so I'm going to take that over there and move it to the other side, and that over there and move it to the other side. What do I get? So I'm going to get the sine of B and if the B is moving from the other side, the B is going to have to be over B equals the sine of C equals over there. Oh, that's quite clever. So that says the sine of an angle divided by the side opposite it is equal to the sine of another angle divided by the side opposite it. And that's essentially the proof of the sine rule. What we often do then is we say, similarly, if we create a line, let's say CE perpendicular to AB, so what would that look like? If we could create a line CE perpendicular to AB, so I'm just going to leave this in for a second. So if we drew in a line that went to there and it was perpendicular, then we could prove the same thing as before, except the only difference is we wouldn't be starting with B and C. We would prove that A, and so we'd prove the sine of A over A is equal to the sine of B over B. So the page is getting a bit cluttered, so I'm just going to take that out for now. But by repeating the same process, just with a different construction, we could then prove what we know to be the sine rule, which basically says this. Which is really, really clever, and it's going to help us to solve a lot of triangles. So let's just have a look at that. So if I think of my acute angle triangle, if I take an angle, so let's talk about, let's give the same numbering as before. So if I choose this angle, for example, then I'm going to say the sine of B. Now what's going to be the side opposite the vertex B? It's going to be the length little b. So the sine of B over B is equal to, let's choose the angle over here, and we're going to say that is equal to, what's opposite that? It's going to be little a over here. And we could have done the same thing for the angle over here and the side over there. And so we actually know that this is a general identity that's true for all acute angle triangles at this stage, and we'll go on to prove the same thing for a acute angle triangle. For an obtuse angle triangle. So let's just see how this would help us solve a triangle. Alright, so using the sine rule, the new mathematics we've learned, let's see how we could apply it to the original triangle from earlier on and use it to solve this triangle. And at this stage, the unknowns are, essentially this side over here and this side over here. Now, it's a good time to mention that the sine rule we've learnt about, which was the sine of A over A equals the sine of B over B equals the sine of C over C, where these are all the angles, can actually be written in two forms. So the one form is to write it with the sine of the angle on top. Now, if that is generally true, you could also write it as the reciprocal of that, where the sides are on top. And that would still be true. So you can think of it this way, if you had something written as 1 over 2 equals 1 over 2 equals 1 over 2, if you flipped everything around and found the reciprocal, you'd then have 2 over 1 equals 2 over 1 equals 2 over 1. The equality will still hold, it's just that everything has been inverted. And sometimes, like in this case, it may be useful to use the sine rule in this other form, because in this case you're solving for the unknown sides, so A, B, or C, and so it's often nice to have them as the numerator. So let's see how we would apply it to this triangle. If I'm trying to find the length AB, the white squiggly line, we could say that, in fact, let's call it little c. So little c divided by the sine of the angle opposite that, so that would be the sine of 70, would be equal to, well, what's the one side that we do know? We know the 2. So what's the sine of the angle opposite that? It's the sine of 30. And if we want to now solve for what c is, we obviously have to move the sine of 70 over here away from it. So what we're going to do is we're going to say that c, let's rather use white, so c is equal to, if I move that sine of 70 to the other side, I'm going to get 2 times the sine of 70 over the sine of 30. And if we punch that into our calculator, that's fairly easy to compute. Now, using the same method, we could have also found the length of the side B. The only difference here would be we'd write B over the sine of 80 would be equal to 2 over the sine of 30, and using the same method we could work out the length of B. So you can see, it's once you know the sine rule, it's quite easy to work out the length of unknown sides if you've got sufficient information. You'll notice that this does not depend in any way on using a right angle, and in fact, if you think back to the proof of the sine rule, the way we got around the original problem was we cut this triangle into two pieces, two triangles that were 90-degree triangles themselves. And so we're kind of using old knowledge but just reapplying it in a new way. So the key now is just to learn how to use this rule and apply it, and the next thing we'll talk about is the ambiguous case of the sine rule.